so we have some problems with hearing each other. So the system will be as follows. During my talk, I will not hear you, but after that, we shall change the system, and it will be possible to exchange remarks, questions, and so on. Okay, so I begin. This is our first try, so anything can happen. I'm going to speak about generalization of a remark made by Luigi Bianchi in his old paper issued in 1892.
Yes, but we see nothing.
This is the paper where he described this permutability theorem for Backlund transformations of the Sine-Gordon equation, and he made the following remark. I'll repeat it on the blackboard, slightly changing the original notation. He deals with the Sine-Gordon equation written in the following form. Sorry.
Anybody sees what happened? Because I see nothing.
This coefficient 2 is inserted to simplify the formulas for the Backlund transformation. And it's Backlund transformation, the classical, the first known Backlund transformation. So this system possesses the following property. If, say, U is a solution of the Sine-Gordon equation, then V found from this system is a solution as well, and vice versa. So this is the classical outer Backlund transformation for the Sine-Gordon equation. And Bianchi notices the following. Assume that U is a solution found from the Backlund transformation. Then it satisfies then it contains some arbitrary constant, say C. Consider the function psi, which is du over this constant and logarithm of this derivative. Then this psi satisfies the following property. consider the form omega then this form is closed. This means that, well, speaking modern language, this means that this form is a non-local conservation law for the Sine-Gordon equation. For example, if V is satisfies the Sine-Gordon equation and U is found by means of the Backlund transformation, then U is a non-local variable, and this is a conservation law that depends on this non-local variable U, or vice versa on V. What I'm going to speak about is that this, well, Bianchi found it just by playing with formulas that arise in the course of his computations, and it is just a byproduct of his main task. And what I'm going to speak about is that this simple observation is of a very general nature. So I'll begin with some generalities. So for us, a differential equation is a submanifold in the space of infinite jets, where pi is a locally trivial vector bundle. And this means that we deal with not equation itself, but with the infinite prolongations. This equation is endowed with the so-called Cartan distribution, which is locally spanned by total derivatives, and moreover, in the bundle, which I also denote by pi infinity, there exists a flat connection, the Cartan connection. In coordinates, this connection takes partial derivatives to the corresponding total derivatives. This connection is flat, which means that if I apply it to the bracket of fields, then it is the same as the bracket of the corresponding lifts. Now we need the notions of symmetries and conservation laws for equations. So symmetry is a vector field on the equation, which is vertical with respect to this projection, which means that it does not contain components of the form and which preserves the Cartan distribution. This means that the following inclusion is valid. Commutator of a symmetry with a vector field from the Cartan distribution again lies in the Cartan distribution. So locally, any symmetry is of the form of evolution vector field where vector function phi satisfies the linearized equation. All this is penalties, but I needed to fix notation. Now, a conservation law on our equation is a horizontal vector differential form of degree n-1, where n is the dimension of the base manifold, that is the number of independent variables. And this form must be closed with respect to the horizontal de Rham differential. Horizontal de Rham differential looks like well, not all conservation laws are interesting. Among them, there are so-called trivial ones. So conservation law is trivial if this form is exact. So actually, the space of conservation laws is the same as the space of n-first horizontal homologies of our equation. Now, the next notion that we need is the notion of differential covering. So consider our equation and consider some locally trivial bundle to this equation. So we have two projections. We say that this bundle is a differential covering if first this is a surjection, and second, for any point theta from this space, the differential of tau at the point theta restricted to the corresponding Cartan plane is an isomorphism from this plane to the corresponding Cartan plane on this equation. So this is a vector bundle whose projection, differential of whose projection isomorphically acts on Cartan planes. In coordinates, this means the following. Consider local coordinates, trivialization of our bundle with fiber-wise coordinates W. Well, if the number of these coordinates is finite, then this L is called the dimension of our covering. Otherwise, the covering is infinite dimensional. And these W's are called nonlocal variables. So the definition of our covering means the following. Consider the total derivatives of this space. Then they should be of the form these are total derivatives on the base equation, and these are some tau vertical vector fields. And tau is a covering if the following system is satisfied. it is easy to see that this condition means that E tilde is the system of equations of the form this is an overdetermined system, and it must be compatible modulo the equation E. Now, all the objects on E tilde will be called non-local with respect to the base equation E. For example, a symmetry of equation E tilde is a non-local symmetry for E. A conservation law of E tilde is a non-local conservation law for E, and so on and so forth. Let us write down the conditions which define non-local symmetries. So they are as follows. First of all, we take linearization of our equation E. It is a differential operator in total derivatives in dxi. So we can lift it to E tilde by writing tildes over all D capital. And we obtain the lift of our L. So any symmetry is defined by a collection of functions phi. Let me check the notation. Which satisfy the system we say that well, by the way, this part of our symmetry is called its shadow. So shadow satisfies just the lifted linearization equation. And we say that symmetry is invisible if it has no shadow. So if phi equals 0, this means that invisible symmetries, which are very important for us, satisfy the system. Invisible symmetries. To proceed, I need one more notion which will be needed for the further discussion. Consider an arbitrary covering it is called linear if first tau is a locally trivial vector bundle, and second, the action of total derivatives here preserves fiber-wise linear functions tilde. This makes sense because we consider a vector bundle. In coordinates, this means that these tails are linear with respect to non-local variables. So with a linear covering, we can associate matrices we are L by L matrices, and the condition to be covering is equivalent to the fact that the following equation holds, where this is the commutator of matrices. So we see that linear coverings are the same as zero curvature representation. Now let's have a look at this definition of invisible symmetries. We see that the equation for invisible symmetries defines a covering. So we had our E, we had our covering tau, and this condition defines a new covering, which I will denote by well, this is I. So the condition for invisible symmetries is actually a zero curvature representation for the covering equation E tilde. Well, let us begin with the one-dimensional case. Well, from now on, I shall assume that we consider two-dimensional equations. First, let omega be a conservation law of our equation. Conservation law means that let us put into correspondence to this conservation law a one-dimensional covering. Obviously, this condition is equivalent to the fact that these two vector fields define a covering structure in this bundle. And vice versa, if we have a covering structure, then such that the tails do not depend on non-local variables, then we obtain a conservation law. But it may happen that this conservation law is trivial, so let us compare triviality of conservation laws with properties of the corresponding covering. Let us say that E is differentially connected if, well, invariantly, if its zero group of horizontal cohomologies coincides with real number. In coordinates, this means that the system of equations has only trivial solutions. We shall now assume that all the equations are differentially connected. And a covering over a differentially connected equation is called irreducible if the covering equation is irreducible as well. This means that if we solve now these equations here, then the result will be the same. Well, now coming back to our situation, we can state that omega is, well, let's denote this covering by tau omega. Omega is non-trivial if and only if omega is reducible. So non-triviality of conservation laws is equivalent to irreducibility of the corresponding coverings. Such coverings we shall call abelian. More exact, one-dimensional abelian coverings. General definition. So general definition is as follows. Let tau be a finite dimensional covering and we say that it is abelian if there exists exactly L non-trivial conservation laws on E such that the lift to the covering equation becomes trivial. In coordinates locally, this means that we can choose coordinates in such a way that the corresponding coefficients will not depend on non-local variables. So general abelian coverings reduce to systems of independent conservation laws of the corresponding dimension. Now, the first result is a straightforward generalization of the observation by Bianchi. Consider a one-dimensional covering. Assume that this covering is irreducible. Then our E possesses either local or non-local conservation law. So we have two options. Either this covering is abelian, then this means that it was constructed by means of a local conservation law, and we have nothing to prove. Assume that it is not abelian. Then let us write down. So this is one-dimensional non-abelian covering. Let us write down the defining equations for our covering. And let us, so this is our tau. And let us now write down the defining equations for invisible symmetries in this covering. That is the equations for tau I. They will be, say, psi x equals psi y x. This is our and the same, this is what Bianchi called an arbitrary constant. So now we see that this is also a covering. So let's denote this logarithm by psi tilde. Now we see that the form is a conservation law for this equation that is non-local conservation law for the initial equation. This is exactly what Bianchi did for the case when E is the sine-Gordon equation and tau is the covering which is associated to this famous Auto-Beckland transformation. But now this can be generalized to the case of coverings of an arbitrary dimension.
So you constructed over covering, you constructed another covering.
Yeah.
Which is what is vertical tangent covering?
Yes, well, this is, I wanted to say it later. This is the vertical part of, so we have E, we have E tilde, we have tangent covering to E tilde, we have to E tilde, we have tangent covering to E, and in this bundle we can take the tau vertical part, and this is exactly what this covering.
And this covering is a linear?
No, this covering is linear.
Yes, yes.
No, but in the case when L equals 1, it is equivalent to an abelian covering by the change and
So it's abelian. So it's abelian.
Yes, actually it is abelian. It looks as if it is not abelian, but it is equivalent to abelian covering. Yeah, exactly. Now let L be arbitrary but finite dimension. Let us say that a covering we always assume that it is irreducible, and let us say that it is strictly non-abelian. If we take an arbitrary conservation law non-trivial on P, then is non-trivial as well. This means that, informally speaking, this covering contains no abelian component. If we had a conservation law, then its lift is also a conservation law. Nothing vanishes. And now the next theorem is that if an equation admits an irreducible covering, then it admits at least one non-local conservation law independently of the value of the dimension. To prove it, I need one lemma and one construction. Tau is strictly abelian and only if its linearization is Well, it's a generalization of an obvious fact. If we have an abelian covering, which means that these terms are independent on W, then it's linearization which is obviously reducible. You can solve this system. And the construction is as follows. Let tau be a linear covering. Then we consider the projectivization of our bundle, standard geometrical precision. We take, and this gives us a covering of rank which is less by one than the initial rank. Well, in coordinates, this construction is quite simple. Let's, for example, take a two-dimensional covering to make computations shorter. So let's consider two-dimensional maybe I'll have a look at my no, it will be shorter in the general form. So let us consider a linear covering, which means that we have the following relations. So this is a system of linear equations which is compatible modulo our equation E. So let us, so this is our tau. Let us choose projective coordinates, for example, in the domain where so we introduce W alpha bar, which is Now we must compute these derivatives. And they are as follows. So this is the condition for our new covering, which is nonlinear, whose rank is and it is almost obvious that if the initial covering was irreducible, then this covering is irreducible as well. Now the procedure. We take an arbitrary irreducible covering of arbitrary finite dimension. We have two options. Either it is not strictly abelian, then it means that there exists a non-trivial conservation law of our equation EU, and we have nothing to prove. If it is not, if it is strictly abelian, then let us consider the covering. This is also covering of rank but this covering is linear, irreducible linear covering. Now let us projectivize it. Давайте это Тау-1, а это будет Тау-2. We have two options. It is either not strictly abelian, then there exists a local conservation law, or it is strictly abelian. Then let us take its linearization. It will be reducible. Let's consider and so on. For a finite number of steps, we shall arrive to a one-dimensional covering, which is either abelian it will, well, and we finish at this step. Or not, then we consider its linearization and come back to the example with which I started. That finishes the result. Now I think a couple of examples. Are useful to present. I have here a lot, but that's well. KDV. Miura transformation. Well, Miura transformation is actually a one-dimensional covering of this form. The covering equation is the modified KDV. Well, this is a non-abelian covering. Let's construct its linearization. It will be of the form psi x equals equals well, it's a particular case of the general picture. If we introduce psi tilde, which is equal to, well, here it's better, 3 logarithm of psi, then we obtain the abelian covering. This is a conservation law of the modified KDV equation and non-local conservation law for the KDV equation. This is the non-local variable for the KDV. Well, and maybe one more example, which shows how projectivization works. Oh, too long. Zero curvature representation for the KDV. Where X and T are the matrices. Well, so also 2 by 2 matrix. So this is a linear covering, 2-dimensional linear covering. So to linearize it makes no sense because linearization of linear covering is second copy of the same covering. So let's try to projectivize it. So let's consider the domain where for example, W2 does not vanish. Let us introduce projective coordinate. And then the projectivized covering will be of the form so this is a nonlinear covering. Sorry. This is a nonlinear covering, and its linearization is Again, consider the new non-local variable. And we obtain the following covering. Which is an abelian one-dimensional covering over the projectivization. So it's a conservation law for the projectivized covering and non-local conservation law for our equation. Well, this is essentially all. Now, if we have to have some discussion, we have to change the setting, yes? Well, so what should I switch off? Просто выключить нельзя. О, нет, сейчас, а вот это. Mute. Off, yes. Наверное, здесь же. Так. А здесь я включаю, да? Okay, so do you hear me or not?
May I ask you a general question not related with your talk?
Меня слышно?
Слышно, слышно.
Отлично. So if you have questions, remarks.
I have general question. I'm terribly sorry. It was almost, okay, maybe it's my problem, but I see almost nothing on the blackboard. I don't know how many people had the same situation as me.
Well,
Technically, it was very difficult for me to see.
Well,
I don't know. Only my problem in this case. I remove my.
This is your problem because we have Alex here, who didn't look at the blackboard, but looked at his computer, and he saw everything. Let's ask someone else.
Okay. No, but on the blackboard I see those. Okay, maybe it's my problem.
But do you see me?
I that says that you. Okay. Забудем все.
Okay.
No problem.
More questions? No question? Okay. Now, well, in our first letter, we kindly asked all the participants to of your talks for the seminar. There was no reaction. Does this mean that no one wants to have a talk? Huh? Again, no reaction, so no one wants.
Now I see Blackboard. Now it's much better. I see.
Of course, because you see it by means of my computer, not by means of.
Yes, but I see it much better than because. Yes, now I see the Blackboard by means of your computer. It's much better. I see the formulae.
Oh, okay.
Because in the first case, I see nothing. I'm sorry. I don't think that's only my problem. Неужели мне такое плохое?
Нет, там дело не пойдет. Нет.
Если вы выбираете спикер.
We understand nothing. It was not speech. Again, if you had a question, try again. Or send a message in the chat. No comments, no questions, no suggestions. Окей. Олег, вам нечего рассказать нам?
Now, not now. Perhaps during the semester.
Okay, clear.
I'll send you a letter when I'll have some to
Perfect.
present.
Okay.
In my turn, I would like to invite you or anyone to make a talk at the seminar of the Department of Applied Mathematics in AGH University of Krakow.
Oh, thank you. We'll
In any oh, sorry, Thursday.
Every Thursday, what time?
Every Thursday. No, starting from perhaps the middle of October. If someone would like to make a talk,
but
contact me.
You should send us a reference.
Oh yeah, I'll send.
Okay, thank you. So no more remarks, questions.
Joseph, I am Raffaele. Can you hear me?
Yes, I hear you.
Do you have open problems?
What do you mean?
Oh,
I hear you, but I don't see you.
sorry?
I hear you, but I don't see you. Now I don't hear you either. So what, Raf? Where are you? I think he tried to switch on video and switched off everything.
Yes.
Yes. So what was your question? Or was it not a question?
I suppose the question was about the open problems in this this topic. Open problems is concerned with this kind of conservation laws, as far as I understand, Raf.
Well, at the moment, I see no open problems.
Sorry, my internet went down.
Oh, that's you, Iraf. So, what was your question?
No, the question is if you can, if you have in mind some open problems to which you can, how to say, apply this construction and find something interesting.
No, at the moment, I see only it as a method to construct non-local conservation laws, starting with an arbitrary, non-trivial covering.
Yes. Okay.
I have other open problems.
Okay.
We can discuss it later.
Yes. Okay. Okay. Thank you.
More questions? So, see you next time.
Okay.
So be healthy. Well, take care of COVID-19.
Yes, and hopefully one day in physical presence.
Oh, I do hope, yes.
Very much.
See you later.
See you.
Bye-bye.
Bye-bye.